Okay, hi. So this is DAA. In this question, what we have is sort of three kind of concepts jumbled together in one question. So it's kind of like a mixture of DAA questions. So in the first part, we have the master's theorem and kind of recurrences in general. And in the second part, we're kind of dealing with heaps. And then in the third one, it's a greedy approach. In the first one, the master's theorem, I kind of have to go through. um, the thing. So like basically it usually follows this format of T of n is equal to A times T of a smaller subproblem, which is divided by something, and then plus C of n to the D, where it is a general form as f of n. So what we do is essentially we compare the cost of the dealing with the recurrences, like the leaves, smaller cases, versus the ones that are at the current step and seeing which one's bigger. So we just compare n to the log b of a and then compare f of n or n to the d and then see which one's bigger. Whichever is bigger, we go by whichever complexity. And if it's the same, we just times log into it. And then, so like we kind of just apply the theorem for the first part. We're asked Tn is equal to 8Tn divided by 2 plus 1. This fits the master theorem exactly. So we just have a equals 8, b equals 2, f of n equals 1. We see that log of b of a is equal to 3, so n cubed is greater than 1, so our complexity is n cubed. Pretty straightforward. For part B, we realize that n minus 1, Tn minus 1 does not fit into the master theorem. So instead, we just expand it out. So then this expression would just be 1 squared plus 2 squared plus 3 squared all the way to k squared. I mean n squared. So then it would just be of the form of something n times 2n plus 1 times n plus 1 divided by 6. So we see that we have something n cubed, so it's theta n cubed. And for part C, what we have is something n to the square root n. So the problem with square root is that we can't deal with it necessarily in the master's form. So we kind of have to change the form slightly. So we're just going to define n to be 2 to the k. And then k, obviously, rearranging would just be log 2 of n. So then over here, what we can do is replace n with 2 to the k, and we would get t to the 2 to the k plus equals 2, 2 times t to the 2 to the kth power divided by 2 plus 1. So then we're just going to define a function that's called sk, which basically takes t to the 2k and change and just take that exponent part. So then we're left with the form of a recurrence that actually looks like the master's form. So like we can apply the theorem with a equals to 2, b equals to 2, and d equals to 0. So we see that log of b of a is greater than 0. So hence our thing would just be O1. So it would be S of k is equal to theta of k. And we remember that k is equal to log 2 of n. So when we plug it back, t of n is equal to s of k. So then it would just be log 2 of n. And then that would just be theta of log n because we don't care about the base, so it's just log n in general. Okay, so we're done with part A. For part B, we're just asked to kind of design a data structure that supports make max heap, insert, extract to max. Make max heap just takes a list, array, and changes it to the heap. Insert just inserts it to the thing, and then extract to max just gets the first and the second max. Show how to modify max heap data structure to achieve this. What is the running time of these three operations? Okay, so let's go over what I have. Here basically let me get to part B. We can leave the ordinary max heap unchanged because we still have a max heap and then the functions actually just use max heap and we can just work from there. So when I was doing the question, I sort of made most of the things were right that I wrote from earlier. As I scrolled down, you could probably see it. But basically, what I missed was the complexity. I said O n log n, but in reality, that is a loose bound. The like a more tighter bound would be O of n. Why was it be like n log n basically came from okay, I have to insert n times, right? And then each time heapify, calling heapify would take log of n. So hence it would be n times log of n. But we can actually do better. So for make max heap, what we can do is we can consider the heap condition, right? The heap condition is when um, something in its like something over here, let's say a node, um, is valid if it's greater than both of its children if they exist. So for our leaf, because they don't have any children, conditions are already satisfied. So hence, the only kind of things that we need to actually check would be the nodes that have children. But if we think about the structure of the heap structure, right, there's only a few elements that are at the top, and the most of the elements are actually concentrated on the bottom, which are the leaves. So that's why we would have O of n would be possible because there are a few elements that we actually need to check. So when we're checking, we're just going to, because we're going to think of it as this, we're implementing the heap using the array. So we're just going to have the first element, the root element is going to be here, and then each one goes down. The children would just be two times whatever it is, and then either that or plus one, sort of like that. And then at the end of the most of the things concentrated here would be the leaves, or with no children. So that would be the case. And what we do is essentially anything over here does not need to be checked, so we don't need to bother with this. And we're just going to work backwards from here and just check that basically these all work from here. And root would be the last element we check. So we know that there are roughly at height h, the number of nodes would be of this value. So, and the time is O of h. So we can write this as T of n is equal to the sigma as h equals 0 all the way to log n of this thing over here that takes O of h time, right? So then we can change it from here. So we have O of n times this. By geometric series, what we can do is we know that anything of x has to be smaller than 1. So over here, our x, we could, if we were to do x of h, it would just be of this expression. And if we were to take the derivative of that, we would get the form of h times x to the n minus 1 would be this thing over here. And if we multiply x to the form we need, we would get this. So in our case, we have exactly this form, except we just substitute x to be 1/2, which satisfies this initial condition over here. And then we would get this. So then this whole thing over here evaluates to a constant 2. So this goes from h from 0 to infinity. So h of 0 to log of n would still be a constant. So hence, we see here we extracted out an n, and this is a constant, so it's O of n. So yeah, the time complexity would be O of n. So this is kind of the actual kind of proof for why it's the case. And then for the insert function, it's pretty straightforward. You put x at the end, and then you call heapify. Putting x at the end takes O1. Calling heapify takes log of n because we just swap it from the bottom up, and the height is log of n, so it takes log of n operations at most. So yeah, so that's why it's log of n. For extract to max, we know that max is at the root. Second max is one of the two children of the root. So finding them takes O1. And then we can do replace root by the last element, size decrease, and then call heapify, and then repeat this with the new root. And then we know that the deleting operation is simply removing it takes O1, and the heapify, when we replace it back, takes O of log n because we just go through the height and put it in the right order. So yeah, so that's log n. So 2 times that would still be log n in terms of complexity. So that doesn't change. That's part B. And then part C, we're asked, we assume that the cost of adding numbers is equal to the value of the result. For instance, 5 plus 6 is 11, and 5 plus 6 plus 8 is 30, because 11 and then 19 is 30. So we want to add the elements of an array of positive numbers using the minimum possible cost. So basically, we would have an array, and then the output is a fully parameterized permutation that has minimum cost. So something like that, give an efficient algo that takes input an array of A as positive integers and returns the way of parenthesizing it, and then analyzes correctness and running time. And then it gives a hint of using a greedy approach and use the heap data structure from part B. So by the time it gives that, I think it's pretty straightforward. Um, let's just go through what I did for. Where is my part C? Okay, here. So basically, I would have an input. This is my input of the arrays, right? And then my output is a fully parameterized equation of the minimum cost. So what I do essentially is I first create a minimum priority queue by inserting every element from A using make heap make min heap. Obviously, I'm not going to be inserting every element. What I'm going to do is I'm just going to call this, and then it's going to do what I just did with the max, but except with the min. So this complexity would actually just be O of it. And then what I do is, um, yeah, basically, I actually define it here. I wanted it to keep it as pairs, but in the actual answer key, you don't need to keep that. I just kept it for the sake of it because I wanted to print it. But in the actual answer key, they actually didn't, what is it called? Print it. They only just kept the cost, which was kind of weird. But if you do want to recover it, you do want to keep the I, so then you store as the minimum priority queue basically takes pairs and rank it by AI, sorted by AI. And then, yeah, so it would still be open. Nothing changes from here. And I'm just going to print in brackets, just for the sake of representing it. So every time I'm going to have the in brackets first, then I'm going to check if pq.size is equal to 0, then return 0. So the idea is that if it's empty, there's not much I can do, so I just return 0, nothing happens, right? And in the case that pq.size is greater than 1, what I would do is I first take m1 and m2, and I'm going to call extract to min. So I'm going to get my two functions, right? And then take it out from the priority queue. And then what I do is I just print m1 plus m2, and I make sure I have a bracket. So the idea behind this is basically every time I want to take the two minimum numbers and add it together because I'll show the correctness later, but it basically is like the best optimal strategy at this point and will be the global optimal strategy as well. And then we just do insert M1 plus M2 back into the thing because we just took it out, right? And then the next one that we're left with in the next round would just be M1 plus M2. And then we just continue this until the size is equal to 1 and we're done at that point. So, in terms of correctness, I guess inside here we have the greedy approach is to pick the two minimum element to plus at any time. So what I said was the problem can be thought of as having n minus one rounds where two numbers are picked and added to the cost, and their sum is added back to the PQ. At any round, the best solution is to minimize the cost would be to pick the two lowest ones from the priority queue because the sum would be the least. Hence, the greedy approach works and is correct simply because if you picked let's say an element M3 that was bigger than M1 and M2 as one of them, on this turn your cost would definitely increase, right? Because M3 is greater than that. And then on the next turn, you will be still left with a bigger number added to the thing, which would leave you with an even bigger option sum if you were to add if it was the second number to be picked, right? So that it propagates. And it doesn't make it any less because if you have a bigger number, like picking the smaller number doesn't you could have picked it earlier and it would have the same result. So it's only equal or worse. So it doesn't improve the situation at all. So that's probably the correctness argument over here. And in terms of the running time, this part is not correct because make min heap would have been O of n because I just proved it. It's the same error if carried forward. And then the second operation of just printing things out would be O1 and checking if it's empty at O1. And then the while loop basically goes through, um, and then I wrote 2 of log x. Basically, 2 of log x is just to call the extract to min from before, right? Because you want to get that. And then you have an O1, which you kind of don't bother with the print. And then the inserting would take O log of X back into the thing. So in total, what we have would be over here would be O of n, and then O of 1 plus the sigma of something of log. But log compared to n would be, it would just be O of n. Yeah, I think I meant basically this part would be O of n. It would just be, let me just write it out fully. So over here we would have O of n. And the O of 1, we can just disregard it because it doesn't change the difference. And then on the right-hand side, we have n times something of log x. So then we would get the form of n log n. So compare n log n is bigger than n, so hence our final complexity would be n log n. So that's the idea. Yeah, I think that brings us to the end of the question. I think this problem was relatively straightforward because when I did this question the first time, yeah, this part was not done well because I kind of forgot how to deal with this case. But overall, like I'd say, as long as you know the master's theorem, you know the heap, how it works, and making sure that you know that it's O of n for this, make heap not O n of log n. I think you're kind of good for this question.